Okay, let's continue then. So we have been looking at this fellow here, and as we saw in the last class, what we have here is not a voltage controlled voltage source, but what kind of a control source? Voltage controlled current source. So this is what we call as the OTA, or the operational transconductance amplifier, and in particular this is a single stage OTA. Now we looked at the DC operating point for this guy. We noticed that although this is asymmetric, as long as you provide common mode excitation, that is both gates have the same voltage so that the VGS is same, then the currents in both branches are equal, and so will be the two drain voltages. And then we went on to find the small signal gain. Now remember, if this was a purely symmetric circuit, we could have found the gain by looking at the common mode part and differential mode part, because for symmetric circuits, looking at common mode and differential mode inputs reduces the circuit to a half circuit. But here, owing to the asymmetry, we didn't take that approach. Instead, we found the gain as product of short circuit GM and R out. And here, recollect, the short circuit GM was the GM of the NMOS transistors, so I'll write it as GM of M2. And the output resistance was R0 of M4 parallel with R0 of M2. So I'll just quickly write it here. Okay, and yeah, and as we saw in the last class, do you think a single stage OTA like this is suited for driving a small resistive load? No, because as we saw, if you have a load resistor, it reduces the small signal gain, so it is not a great choice. So it is often preferred for driving capacitive loads. And we already know we need such high gain op amps and OTAs to be used in negative feedback. So we decided to see what will happen when I have this OTA driving a capacitive load when I use a negative feedback. So something like this. And before that, we saw how do we feed the inputs here. So along with the small signal VI, we obviously have to feed in a bias signal. And in the last class, we saw that instead of specifying the range for VB and VI, which will change depending on the negative feedback circuit that you are using, the practice is to mention the range for the inputs and the outputs of the op amp. And in particular, we noticed that when we use in negative feedback, the inverting and non-inverting terminals are at the same potential, so the differential part is 0. So we only specify limits for the common mode input and the output. And once you know the range for the common mode input and the output, in your specific negative feedback circuit, you can find what is this VICM and Vout in terms of VBVI. So if you know the ranges for these two fellows, you can basically back calculate what is the range of voltages you can have for these two, right? So now we know how to bias this guy properly. So let's see what will happen when I use it in negative feedback. So let's say I have this OTA here. Again, I'm using a negative feedback like this, driving a capacitive load CL. And let's assume that it is all biased properly. I'll only look at the small signal. I'll not keep writing all the bias voltages. And to start with, let's even assume that we have an ideal OTA. By ideal OTA, I mean that the intrinsic output resistance of this guy is infinity. Okay, so I'll mark it here. Remember, the typical symbol for an OTA is this. So you have this quadrilateral and R out. There was some confusion in the last class. To clear it, when I say this GM is essentially the short circuit GM, which is this fellow. And when I write it as R out, that is the intrinsic output resistance, which is in this circuit R02 parallel R04. Okay. So for our initial discussions, let's ignore R out. And let's assume that I apply a small step delta V. Okay. The small signal step is applied delta V of t. Assume that the capacitor CL is initially uncharged. So now can you tell me, and this is V out, by the way, V out of t. So now can you tell me what will be V out of 0 plus? Do you think the output voltage will instantaneously change and become delta V, or will it not? Huh? Why not? Okay, capacitor takes time. Huh? It is okay, but not very compelling argument. Huh? Okay. Okay, so let's see, right? If the capacitor voltage has to change instantly, which means what I'm saying is the capacitor voltage sees a step jump. If the voltage is like this, how should the current flowing through the capacitor be? IC dV by dt, the current must be an impulse. So if I say, okay, maybe I'll mark it cleanly. Hold on, let me make some space. Let me call this as I out. So which means my current I out must be an impulse. But here, can you tell me what is I out of t? Or let me ask you this way, right? So we know if the capacitor voltage should change instantly like this, current must be an impulse. So do you think we can have impulsive current here? Why not?
Because voltage is not infinite.
Yeah. So remember, the OTA itself does not have any limits on how much current it can provide, but the current here depends on what? Is the current? It depends on the input voltages. So it is GM times what is it? The non-inverting minus the inverting, delta V U of t, right? So if I out of t must be an impulsive current, one of these two must be an impulse, but that's not what we have in our circuit. We assume V out to be a step. So obviously by contradiction we can clearly show that the capacitor voltage cannot change instantaneously. So what is V out of 0 plus then? So what is V out of 0 plus? 0, assuming that it was initially uncharged. Okay. So then what is I out of 0 plus? From here, what is I out of 0 plus? GM times? Oops, sorry. Oops. GM times what? Delta V. Fine. That's it. So is this clear? I've just used simple contradictory arguments to show that the voltage here cannot change instantaneously. Okay. Great. So now let me try to sketch V out of t. So x-axis is time. I'll not show it explicitly. So let us say V out to 0 and this is t equal to 0. At 0 plus it is still 0. So this is V out of t. Okay. And at 0 plus I have a current GM delta V pushed into the capacitor. So what will happen to the capacitor voltage? It will start increasing. So now the output voltage V out increases. So what will happen to the current? Current reduces. So the current pushed into the capacitor reduces. So what can you say about the rate at which the capacitor voltage increases? The current is dropping, so the rate reduces. So this has happened. And how will be the curve finally? How will the curve look like finally? It's an exponential thing. Okay. And eventually it reaches delta. Okay. Again, this is your first order RC settling behavior, right? And what will be V out in steady state? What is delta V? And what can you say about I out in steady state? 0. Right? That's the only state in which this can lock, because if I out was still non-zero, the voltage will keep increasing. So the this is the final steady state. Great. So yeah, as you know, this is a first order settling behavior. So if I were to write a closed form expression for V out of t, what are the 3 pieces of information I'll need to write the capacitor voltage in, let us say, a first order circuit like this? What are the 3 pieces of information I'll require? Initial voltage, final voltage, and the time constant. So I know the initial final voltage. Let's try to find the time constant. And okay, how do you find the time constant? Huh? And time constant is essentially the capacitance times the effective resistance it sees. So I have, let me just redraw this here. Okay. So I need to find the effective resistance looking here. I'll short all the other inputs. So how do you find the effective resistance now? Huh? Yeah, I mean the same old, you apply V test. You apply test voltage here, this is also at V test. What can you say about this current? Minus GM or plus GM? Minus GM. So which means the current flowing from right side to the left side is what? Okay. So what is the looking in resistance, equivalent resistance? 1 by G. So the time constant is the capacitance times the resistance, which is CL by GM. Okay. Let me write it here again. Again, this shouldn't be surprising, right? So if we have, let us say, an NMOS transistor and I connect its gate and drain, what is the effective resistance here? 1 by GM, right? It's the same thing, isn't it? So here, this is also a VCCS. This is the negative terminal, this is the positive terminal, this is the output. Same old thing. Great. Is this clear? So if I were to write it, V out of t, it is delta V times 1 minus e power minus t by tau times u of t. Okay. So what we'll do now is let's try to compare what will happen if I have an ideal op amp instead of an ideal OTA, right? This is when we have an OTA or a VCCS. So let's quickly redo the calculation and see what will happen if I had used an op amp or a VCVS in place. Okay. So again, the same circuit, I am using a VCVS instead. CL, and this is again delta V times U of t. Yeah. So here again, let's assume that this has infinite gain. So what do you think will happen to V out of 0 plus? Do you think the capacitor voltage here will change instantly? Will the capacitor voltage instantaneously become delta V, or just like this it will be 0 plus? I mean, will it be 0 at 0 plus? It will be 0. Okay, why? I mean, think about it. Here, the way we argued was if the capacitor voltage has to change instantly, current must be an impulse. But this current depends on these two voltages. Correct? And since neither of the two voltages were an impulse, the current cannot be an impulse. Whereas look at this fellow. This current, if this current has to be an impulse, it can be. The current here is coming from a voltage source, right? This is a voltage controlled voltage source. The current provided by the voltage source can be anything in the world to keep the voltage to the required value. Unlike in an OTA where the current indeed depends on some other voltage, here the current can be anything. Fine. So here what will be V out of 0 plus? Delta V. Okay. I mean, if this is not clear, you do it this way, right? Let us say this has a gain of A. This is V out of t. Can you tell me what is V out of t in terms of the inputs? Output is the gain A times the non-inverting terminal delta V U of t minus the inverting terminal, which is V out of t. Now this was an ideal op amp. This tends to infinity. Now I know that this entire thing is negative feedback. So I can be sure that V out is finite. So this fellow is finite. I'll write it because we have negative feedback. So which means this should tend to. Okay. So which means here V out of t will be exactly equal to delta V U of t. So if I were to sketch it now, V out of t will look like this. Okay. So this is what will happen if you have a VCVS, but when you have a VCCS, it exponentially charges with a time constant of CL by GM. Okay. So this is one main difference between using a VCVS and a VCCS. Okay. So to maybe elaborate on this a bit more, let me copy this. I'll erase the waveforms. Hopefully the waveforms are fine. See, let us say you have, oops. Okay. Yeah, say I have a VCVS like this. Okay. And let us say the gain of this fellow is some A. Now, which means the voltage gain from the input to the output is A, and this is, let us say, A. And now let us say I go and introduce some load here, could be any load. If I introduce a load at the output, will the gain from the input to the output change? No, it is a voltage source, doesn't matter what you put there. So the gain is still A. Okay. Now, if this was an ideal op amp, this gain will tend to infinity. Same will be the case here. And when I say it tends to infinity, the gain is infinity across all frequencies, right? Irrespective of what you put at the output, the gain is made infinity across all frequencies. So that's why this is one single number A, which is infinity. Since it is infinity across all frequencies, this fellow can respond instantaneously and change the output to the step delta V of t. Okay. Now let's look at the OTA case. So let us say you have an OTA, and let us say you designed an extraordinary OTA which had an infinite output resistance. Okay. So when I don't have any other load, what is the voltage gain from the input to the output? What is the voltage gain from the input to the output? Infinity GM times R out. R out is what? Infinite. So the gain is, and this is infinity across all frequencies, right? Now let us say I take a nice small capacitor and put it here. So now do you think the voltage gain will be infinity across frequencies? Why or why not? How many think the gain will still be infinity across frequencies? Okay. So see, this is a VCCS. So what is fixed by this VCCS? So the current here is fixed irrespective of what you have. But what is the voltage finally? The voltage here is the current times the impedance here, right? So voltage gain will depend on what load you have. Is that clear? I mean, this is one reason why we told we don't want to use our OTA with a resistive load. Correct? So if I have a capacitor, what can you say about the gain at DC? Infinite, because for DC the capacitor is loosely open circuit, so this is infinity. What can you say about the gain at infinitely large frequencies? 0, because capacitor behaves like a short circuit. 0. So now you see that although the OTA itself had infinite gain across frequencies, the moment it's driving a capacitor, the gain changes as you increase the frequency. Clear? So now you see the gain at DC is what is infinity, right? So since only the DC gain is infinity, only in steady state the output voltage here will match what you have here. Okay. So maybe we'll mention, so the output at infinity will match what is the out of infinity here. Okay. But let us say I look at 0 plus. When I am looking at t equal to 0 plus, do you think I am looking at very small frequencies or very large frequencies? T equal to 0 plus, do you think it corresponds to a small frequency or large frequency? I mean, very small change in time. Frequency, loosely speaking, it's the inverse, so it's infinitely large frequency. Fine. For infinitely large frequencies, what is the gain? 0. So which means now at t equal to 0 plus, this fellow will not be able to respond instantly. So which means the virtual ground will not be established instantly, unlike here. So that's why this fellow takes some time, and so V out of 0 plus will not change instantly. Is it clear? Okay, so now let me ask this. So now look at this equation. This is always true. I out of t is this, right? Now from this equation, let us say I want my V out to change instantly and become delta V, right? When will that happen? When GM is infinity, right? Again, it's a negative feedback. All currents, voltages are finite. This is guaranteed to be finite. So if GM tends to infinity, then my V out of t will be exactly delta V U of t. So that is something to note. We'll remark it here. If GM tends to infinity, my V out of t will be delta V of t. So if GM tends to infinity, then this responds instantaneously, like how we have for an ideal op amp.
We were just talking about impulsive current. Right?
Correct, correct.
So IO can also be infinity and GM can also be infinity with the difference being finite.
IO can also be infinity and
GM can be infinity.
correct. Yeah.
With the difference in voltages being finite.
Yeah.
So
No. What I'm saying is, I mean, I out of t is an impulsive current, right? Impulsive current is essentially, I mean, you think of it like this, right? If you have voltage source, or what I'm saying is this can be an impulse current now. That's all. It instantaneously charges the capacitor. The other way to see is, if it's too confusing, see, I know that if I have a finite GM, right, it output exponentially charges with a time constant of CL by GM, right? Now if I were to make sure that the output charges very fast, GM should be small or GM should be large? Should be large. So limiting case is when you make GM to infinity, that it responds instantly and the output jumps up to the step. Fine. So this is one main difference between VCVS and VCCS. Okay.